There is a galaxy so massive that by all the laws of physics we understand, it should have torn itself apart billions of years ago. It contains more dark matter than we thought possible, more stars than seem reasonable, and it spins so fast that every calculation says it should fling its contents into the cosmic void like a broken centrifuge. Yet there it sits, serene, intact, defying everything. Tonight, we'll journey to this impossible place, explore what holds it together when it shouldn't hold together at all, and discover what this cosmic rebel might be telling us about the very nature of reality itself. It's a story of invisible forces, mathematical limits pushed beyond breaking, and a universe that refuses to follow its own rules. If you enjoy exploring these cosmic mysteries that challenge everything we think we know, your like and subscribe help us continue these journeys together into the impossible. Now, let's visit the galaxy that shouldn't exist. What if I told you there exists a cosmic structure so fundamentally wrong that its very existence breaks every law of physics we understand? Deep in the constellation Coma, 330 million light-years from Earth, floats an object that should not be possible. Dragonfly 44 appears as nothing more than a faint smudge against the darkness, barely visible even to our most powerful telescopes. Yet this ghostly apparition contains 1 trillion times the mass of our Sun. Picture that number for a moment. 1 trillion. That means if you counted 1 solar mass every second, without stopping for food or sleep or rest, you would need 32,000 years to reach the total mass contained within this impossible galaxy. Dragonfly 44 stretches across the same vast distances as our own Milky Way, spanning 100,000 light-years from edge to edge. But here lies the mystery that keeps astrophysicists awake at night. This galaxy produces only 1% of the light our Milky Way generates. 1%. Imagine walking through a city at midnight where only 1 streetlight in every 100 actually works. That gives you some sense of how dim this cosmic giant truly appears. Now consider the physics that should govern such an object. Every galaxy spins through space like a cosmic merry-go-round. Stars orbit the galactic center in vast circles, held in place by gravity pulling inward while their motion carries them outward. Without sufficient mass to provide gravitational glue, centrifugal forces should fling every star into the emptiness between galaxies. Think of a figure skater spinning with arms outstretched, then releasing their grip on reality itself. According to every calculation we can perform, Dragonfly 44 lacks the visible matter necessary to hold itself together. Its few scattered stars should have dispersed into space billions of years ago, leaving behind nothing but cold, empty darkness. Yet somehow, impossibly, this galaxy endures. Night after night, astronomers point their instruments toward Coma and find Dragonfly 44 exactly where it should be, spinning serenely through space as if mocking our understanding of cosmic mechanics. The galaxy contains roughly the same total mass as our own Milky Way, yet harbours only 1% of the stellar population. Where has all that missing matter gone? What invisible force prevents this cosmic structure from tearing itself apart? Scientists have identified something they call dark matter, a mysterious substance that interacts with normal matter only through gravity. In most galaxies, dark matter comprises roughly 80 to 90% of the total mass, but Dragonfly 44 pushes this proportion to an extreme that challenges everything we thought we knew about galaxy formation. 99.99% of its mass exists in a form we cannot see, touch, or directly detect. This means that for every single atom of normal matter within this galaxy, there exist 10,000 particles of something else entirely, something that bends space and time around itself while remaining completely invisible to every instrument humans have ever constructed. The implications stagger the imagination. We live in a universe where the vast majority of matter consists of particles that might be flowing through your body at this very moment without triggering the slightest sensation. These ghostly constituents of reality shape the architecture of galaxies, determine the fate of stars, and govern the evolution of cosmic structure across billions of light years. Yet they remain as mysterious to us as consciousness itself. Dragonfly 44 represents the most extreme example astronomers have discovered of this cosmic magic trick. Here stands a galaxy that appears almost entirely constructed from invisible scaffolding, with just enough normal matter sprinkled throughout to catch starlight and reveal its presence to our searching telescopes. But how did such an impossible structure come into being? What forces shaped its formation in the early universe? And what does its existence tell us about the fundamental nature of reality itself? These questions drive us deeper into the cosmic mystery, where the invisible holds the visible in its ghostly embrace. How can an object weighing 1 trillion solar masses continue spinning for billions of years when the laws of physics demand it should have disintegrated long ago? To understand why Dragonfly 44 represents such a profound violation of cosmic order, we must first grasp the fundamental forces that govern rotating systems throughout the universe. Picture yourself swinging a ball attached to a string in circular motion above your head. The faster you spin, the harder you must grip that string to prevent the ball from flying away. This simple demonstration reveals the eternal battle between centrifugal force, which pushes objects outward during rotation, and whatever mechanism holds them together. In planetary systems, gravity from massive central stars provides the invisible string that keeps worlds locked in their orbits. Mercury races around our Sun at nearly 50 kilometers per second. It remains safely bound because solar gravity pulls inward with precisely the strength needed to balance its orbital motion. Remove the Sun, and Mercury would instantly shoot off into interstellar space along a straight line, never to return. Galaxies face the same physical challenge, but on scales that dwarf human comprehension. Stars within galactic disks orbit their central regions at velocities approaching hundreds of kilometers per second. These cosmic bullets require enormous gravitational anchors to prevent their escape into the void between galaxies. So Isaac Newton gave us the mathematical tools to calculate exactly how much mass any rotating system needs to remain stable. His inverse square law states that gravitational attraction decreases rapidly with distance, falling off proportionally to 1 over the square of the separation between objects. This means doubling the distance reduces gravitational pull by a factor of 4. Apply these equations to galactic rotation, and you discover something deeply troubling about structures like Dragonfly 44. When astronomers count up all the visible stars, gas clouds, and dust within this galaxy, they find roughly 10 billion solar masses of observable material. But their calculations reveal that maintaining stable rotation against centrifugal forces requires at least 1 trillion solar masses of gravitating matter. The visible components provide only 1% of the gravitational muscle needed to hold this cosmic structure together. Imagine a centrifuge in a medical laboratory spinning at maximum velocity with its safety mechanisms completely removed. Under normal circumstances, such a machine would tear itself apart within seconds, scattering metal fragments across the room with devastating force. Yet, Dragonfly 44 resembles exactly this scenario. A broken centrifuge that somehow continues spinning perfectly after 4.6 billion years of rotation. The mathematical impossibility becomes even more striking when you consider the distribution of matter within this galaxy. Most of its visible stars cluster near the central regions, where their combined gravity can actually influence nearby objects. But rotation curves reveal that stars in the outer reaches move just as fast as those closer to the galactic core. This flat velocity profile violates everything Newton taught us about orbital mechanics. In a solar system, outer planets crawl along their orbits much slower than inner worlds because they feel weaker gravitational pull from the distant central star. Neptune takes 165 Earth years to complete a single orbit, while Mercury finishes 4 circuits annually. This relationship between distance and orbital velocity represents a fundamental consequence of how gravity operates across space. Galaxies should follow identical patterns. Stars near galactic centers should race through their orbits, while those at the edges should plod along at leisurely speeds. Instead, observations consistently show that galactic rotation curves flatten out, maintaining constant velocities regardless of distance from the center. This phenomenon first came to light through the pioneering work of astronomer Vera Rubin during the 1970s. Using sensitive spectrographs, she measured the Doppler shifts of light from gas clouds orbiting within spiral galaxies. Her data revealed flat rotation curves across dozens of different galactic systems, each one defying Newtonian expectations. Initially, many scientists suspected observational errors or incomplete understanding of galactic structure. Perhaps hidden concentrations of normal matter lurked in regions too dim to detect directly. but decades of increasingly sophisticated measurements have only strengthened the original findings while extending them to hundreds of additional galaxies. The evidence now overwhelmingly supports a conclusion that challenges our most basic assumptions about cosmic architecture. Either our understanding of gravity breaks down completely on galactic scales, or the universe contains vast quantities of invisible matter that interacts with normal material only through gravitational attraction. What drives human beings to peer deeper into mysteries that stretch our minds beyond comfortable limits and force us to question the very foundations of reality itself? Tonight, we embark together on an extraordinary expedition into the hidden architecture that shapes our cosmos, a journey that will reveal how the majority of existence remains completely invisible to our senses yet governs everything we can observe. If you find yourself drawn to cosmic puzzles that overturn established scientific principles, if you feel that electric thrill when confronted with phenomena that should not exist according to our current understanding, then this exploration will satisfy your deepest curiosity about the universe we inhabit. Over the next 30 minutes, we will unravel the greatest detective story in modern astrophysics, following clues that lead us from impossible galaxies to the fundamental nature of matter itself. Together we will discover how astronomers first stumbled upon evidence for invisible cosmic scaffolding, how they developed ingenious methods to map structures that emit no light, and what their findings reveal about the true composition of everything around us. Your engagement with these ideas, your willingness to grapple with concepts that challenge intuition, helps support our continued investigation into the most profound questions facing science today. Each gentle tap of the like button, each soft click on subscribe, enables us to delve deeper into cosmic enigmas that expand human knowledge and push the boundaries of what we thought possible. These simple gestures of support allow us to invest countless hours researching cutting-edge discoveries, translating complex scientific papers into accessible narratives, and crafting explorations that honor both rigorous accuracy and genuine wonder. When you choose to join this community of cosmic explorers, you become part of a larger mission to illuminate the darkest corners of universal mystery and share those revelations with curious minds everywhere. We will trace the detective work that led scientists from puzzling galactic observations to revolutionary theories about dark matter, following each breakthrough that brought us closer to understanding why structures like Dragonfly 44 can exist despite violating basic physics. Our investigation will take us inside the most sensitive instruments ever constructed, machines capable of detecting individual particles of invisible matter as they drift through underground laboratories buried deep beneath mountain ranges. We will explore computer simulations that model cosmic evolution across billions of years, revealing how invisible matter particles clumped together in the early universe to create the gravitational wells that eventually gave birth to stars and galaxies. Along the way, we will encounter competing theories that attempt to explain galactic rotation without invoking mysterious dark matter, examining alternative proposals that modify our understanding of gravity itself rather than populating space with unseen particles. These intellectual battles illuminate how science progresses through careful observation, creative hypothesis formation, and rigorous testing of competing ideas against the unforgiving standard of experimental evidence. Through this journey, you will gain intimate familiarity with the most exotic objects in the known universe, from ultra-diffuse galaxies that appear as cosmic ghosts to dense dark matter, halos that dwarf the visible structures they contain. We will visit galaxy clusters where dark matter reveals its presence through gravitational lensing, bending light from background objects into multiple images that allow astronomers to map invisible mass distributions with extraordinary precision. Our exploration will culminate in a profound meditation on what these discoveries mean for our understanding of existence itself, connecting the cosmic scale to deeply personal questions about consciousness, meaning, and our place within the vast web of reality. By the end of this expedition, you will possess tools for contemplating the universe that extend far beyond simple facts and figures, frameworks for appreciating both the breathtaking scale of cosmic mystery and the remarkable human capacity to illuminate that darkness through careful investigation and bold theoretical leaps. The invisible architecture we will uncover tonight surrounds you at this very moment, flowing through your body and shaping the destiny of every star you can see in the night sky. Dark matter particles may be streaming through this room as you watch, carrying within their ghostly interactions the keys to understanding how galaxies formed, why the universe looks the way it does, and what fundamental forces govern the behavior of matter across all scales, from the quantum to the cosmic. This knowledge awaits your exploration, ready to transform your perspective on everything from the ground beneath your feet to the farthest reaches of observable space, connecting your personal existence to the grandest story ever told about the nature of reality. How do you discover something that has been staring humanity in the face for centuries yet remained completely invisible until someone built exactly the right kind of eyes to see it? The story of finding Dragonfly 44 begins not with a massive space telescope or billion-dollar observatory, but with an ingenious contraption assembled from telephoto camera lenses that most photographers would recognize from sporting events or wildlife photography. In 2014, astronomers Peter Van Dokkum from Yale University and Roberto Abraham from the University of Toronto faced a frustrating problem that had plagued their field for decades. Traditional telescopes excelled at capturing bright, compact objects like stars and distant quasars, but they systematically missed faint, extended structures that might be lurking throughout the cosmos. These instruments concentrated light so efficiently that diffuse objects simply vanished into the background noise, becoming invisible despite potentially enormous size and significance. Van Dokkum and Abraham realized they needed a completely different approach, something that could detect extremely low surface brightness features across wide fields of view. Their solution appeared almost comically simple compared to the sophisticated machinery typically associated with cutting-edge astronomy. They mounted 8 commercial Canon telephoto lenses, each with a focal length of 400mm, onto a single tracking mount that could follow celestial objects across the night sky. This bizarre-looking contraption, dubbed the Dragonfly Telephoto Array, cost roughly the same as a luxury automobile rather than the hundreds of millions required for conventional observatories. The secret lay in how these lenses handled scattered light, the greatest enemy of faint object detection. Most telescopes suffer from internal reflections that create subtle halos around bright stars, washing out nearby dim features. The Dragonfly Array used lenses specifically designed to minimize such artifacts, allowing astronomers to detect surface brightness levels nearly 100 times fainter than previous surveys had achieved. When Van Dokkum and Abraham first pointed their unusual telescope toward the Coma Cluster in 2015, they expected to find perhaps a handful of previously overlooked galaxies. Instead, their images revealed 47 mysterious objects that defied every expectation about galactic structure. These cosmic phantoms appeared as barely perceptible smudges against the star-filled background, so faint that earlier surveys had dismissed them as imaging artifacts or instrumental noise. The research team coined the term ultra-diffuse galaxies to describe these enigmatic structures. Each one stretched across distances comparable to the Milky Way, yet contained only a tiny fraction of the stellar population found in normal spiral galaxies. They resembled cosmic cotton balls, vast but nearly transparent, as if someone had taken ordinary galaxies and diluted their contents by factors of hundreds or thousands. Dragonfly 44 stood out even among this collection of oddities. Initial measurements suggested it might be the largest and most massive member of the newly discovered population. Unlike the others, which appeared to contain relatively modest amounts of dark matter, this particular object seemed to possess gravitational influence far exceeding what its visible stars could provide. The galaxy had been hiding in plain sight for generations of astronomical observation. Major sky surveys had repeatedly imaged the same region of space, using some of the most powerful telescopes ever constructed, yet none had recognized the presence of these ghostly structures. They existed in a kind of observational twilight zone, too faint for conventional detection methods, but too large to ignore once properly revealed. This discovery fundamentally challenged astronomers' understanding of galaxy formation and evolution. Theoretical models predicted that such enormous yet diffuse structures should be extremely rare, if they could exist at all. The fact that Van Dokkum and Abraham found dozens within a single cluster suggested that ultra-diffuse galaxies might represent a common but previously hidden component of cosmic architecture. The implications rippled through the astronomical community as researchers scrambled to re-examine archived data from previous surveys. How many other cosmic structures had been overlooked due to technological limitations or observational biases? What other surprises might be waiting in regions of parameter space that existing instruments could not probe effectively? The Dragonfly discovery demonstrated how scientific breakthroughs sometimes emerge not from incremental improvements to established techniques, but from radically different approaches that reveal entirely new categories of phenomena. What happens when the most sophisticated instruments on Earth reveal measurements so extreme they force scientists to question everything they thought they understood about cosmic mechanics? After discovering Dragonfly 44 through their innovative telephoto array, Van Dockum and his colleagues faced the daunting task of determining exactly what kind of object they had found. The faint smudge in their images could represent anything from a nearby cloud of interstellar dust to an extraordinarily distant galaxy cluster. To unlock its door, secrets, they needed to measure something that seems almost impossible to detect: the motion of individual stars within this ghostly structure. The team turned to the W.M. Keck Observatory atop Mauna Kea in Hawaii, home to twin 10-meter telescopes that rank among the most powerful optical instruments ever constructed. These mechanical giants gather light with mirrors spanning 33 feet in diameter, collecting photons with such efficiency that they can detect candle flames from distances exceeding 20,000 miles. Even with such incredible sensitivity, studying Dragonfly 44 pushed these instruments to their absolute limits. Over 6 consecutive nights, astronomers used the Keck 2 telescope equipped with the deep imaging multi-object spectrograph to capture spectra from the galaxy's faintest stars. Each spectrum revealed telltale fingerprints of stellar atmospheres, absorption lines created when specific elements block narrow wavelengths of starlight. More crucially, the key, precise wavelengths of these lines carried information about stellar velocities through the Doppler effect, the same phenomenon that changes the pitch of an ambulance siren as it races past. The measurements that emerged from this painstaking analysis defied every expectation. Stars within Dragonfly 44 exhibited a velocity dispersion of 33 kilometers per second, meaning individual stellar orbits varied by this amount from the galactic average. While this might sound modest compared to typical highway speeds, it represents enormous kinetic energy when applied to objects weighing as much as our Sun. These stellar velocities indicated that something invisible but incredibly massive was gravitationally accelerating stars to speeds far exceeding what the visible matter could sustain. Even more surprising, the team detected no systematic rotation whatsoever within the galaxy. Unlike spiral systems where stars follow orderly circular orbits around a central axis, Dragonfly 44 appeared essentially static from a rotational perspective. Its stars moved in random directions with no preferred orientation, as if the entire structure existed in a state of gravitational equilibrium maintained by some unseen architecture. To put these velocity measurements in perspective, consider that our own Sun orbits the Milky Way center at roughly 220 kilometers per second. This motion results from the combined gravitational pull of hundreds of billions of stars, plus enormous quantities of gas, dust, and dark matter. For stars in Dragonfly 44 to achieve velocities approaching 1/6 of this value, while orbiting within a galaxy containing only 1% as much visible matter, seemed physically absurd. The team calculated the mass-to-light ratio needed to explain these observations, arriving at a value 26 times higher than typical galaxies exhibit. This meant that for every solar mass worth of starlight, Dragonfly 44 required 26 solar masses of gravitating material to maintain stability. Normal galaxies show mass-to-light ratios between 3 and 5, already indicating substantial dark matter content. Dragonfly 44 pushed this proportion into completely unexplored territory. Complementary observations using the 8-meter Gemini North telescope revealed additional shocking details about the galaxy's structure. High-resolution imaging detected roughly 90 globular clusters scattered throughout the outer regions, far more than expected for such a dim system. These ancient stellar groupings typically form only around massive galaxies, suggesting that Dragonfly 44 might be a failed version of something originally destined to become as large and bright as the Milky Way. The spectroscopic data painted a picture of cosmic architecture unlike anything previously documented. Here was a galaxy-sized structure, where invisible matter outweighed visible components by factors approaching 1,000 to 1. The few scattered stars served merely as tracers, revealing through their motions the presence of vast gravitational scaffolding that remained completely hidden from direct observation. Roberto Abraham captured the profound implications when he noted that stars were moving far too fast for such a dim collection of light, as if the galaxy possessed some kind of gravitational secret that allowed it to accelerate matter well beyond the limits imposed by its visible contents. What does it feel like when decades of careful research suddenly collide with observations so extreme they shatter fundamental assumptions about how the universe operates? When Roberto Abraham first examined the velocity dispersion measurements from Dragonfly 44, he experienced what can only be described as scientific vertigo, that disorienting moment when established theories crumble beneath the weight of undeniable evidence. The numbers staring back at him from computer screens told an impossible story. Here was a galactic structure, containing so few stars that basic gravitational physics demanded it should have disintegrated billions of years ago, scattered into the cosmic void like leaves blown apart by hurricane winds. Abraham found himself confronting a paradox that challenged everything astronomers understood about galactic stability and formation. The visible stellar population within Dragonfly 44 provided roughly 1% of the gravitational binding energy required to maintain structural integrity against the disruptive forces of stellar motion. This meant that 99% of the galaxy's gravitational influence originated from completely invisible sources, a proportion so extreme that it pushed the boundaries of theoretical possibility. Abraham realized he was looking at evidence for the most dark matter-dominated galaxy ever discovered, an object that existed primarily as invisible architecture with just enough normal matter sprinkled throughout to catch starlight and reveal its presence to human observers. The implications hit him like a physical blow. This was not simply another unusual galaxy, but potentially a completely new category of cosmic structure that existing formation models could not explain or predict. Meanwhile, Peter van Dokkum wrestled with equally profound questions about the fundamental processes that govern galactic evolution. His team had uncovered something that should not exist according to current theoretical frameworks, yet there it sat in their images and spectra, as real and undeniable as any astronomical object ever detected. Van Dokkum found himself in the uncomfortable position of announcing a discovery that he could not fully comprehend, admitting publicly that they had no idea how galaxies like Dragonfly 44 could have formed through any known evolutionary pathway. The admission represented more than scientific humility. It acknowledged that their findings had revealed gaps in human understanding so significant that entirely new, theoretical approaches might be necessary to explain what they had observed. The dramatic discrepancy between visible matter content and gravitational effects within Dragonfly 44 exceeded anything previously documented in astronomical literature. While most galaxies show dark matter ratios between 80 and 90%, this object pushed the proportion to 99.99%, creating what amounted to a natural laboratory for studying invisible matter in its purest form. The few scattered stars functioned essentially as test particles, revealing through their orbital motions the shape and density of gravitational fields produced by completely undetectable components. Van Dokkum recognized that they had stumbled upon the cosmic equivalent of a fossil, a relic from the early universe that preserved conditions and processes no longer active in contemporary galactic formation. Word of the discovery spread rapidly through the international astronomical community, generating reactions ranging from excitement to skepticism to outright disbelief. Conference presentations featuring Dragonfly 44 data drew standing room-only crowds as researchers struggled to reconcile the observations with established theoretical predictions. Some scientists questioned whether systematic errors in the velocity measurements could account for the extreme mass-to-light ratios, while others wondered if the object might represent something other than a genuine galaxy altogether. The most unsettling aspect for many astronomers was not simply that Dragonfly 44 violated expectations, but that it did so by such enormous margins that incremental adjustments to existing theories seemed inadequate. This was not a case where slight modifications to formation models could accommodate new observations. Instead, the discovery demanded fundamental reconsideration of how massive structures assembled in the early universe, and what physical processes determined their ultimate composition. The scientific community found itself confronting the possibility that conventional wisdom about galactic evolution might be incomplete in ways that had previously been unimaginable. Van Dokkum and Abraham had achieved something simultaneously thrilling and terrifying for any researcher. They had opened a door to entirely unexplored regions of cosmic parameter space, revealing phenomena that existing knowledge could neither predict nor fully explain. Their discovery represented the kind of paradigm-shifting breakthrough that occurs perhaps once in a generation, fundamentally altering how scientists think about the architecture and evolution of galactic structures throughout the universe. What fundamental principles govern the motion of celestial bodies throughout the cosmos? And why do these universal laws seem to break down completely when applied to galactic structures like Dragonfly 44? To understand the profound mystery posed by ultramassive galaxies, we must first examine how orbital mechanics should work according to centuries of established physics. Johannes Kepler discovered in the early 17th century that planetary motion follows precise mathematical relationships, patterns so reliable that modern spacecraft navigation depends entirely upon their accuracy. His third law reveals that orbital periods increase dramatically with distance from a central, gravitating body, meaning outer objects crawl along their paths while inner ones race through space at breakneck velocities. Consider our own solar system as a perfect demonstration of these principles in action. Mercury, the innermost planet, screams around the Sun at 48 kilometers per second, completing its orbit in just 88 Earth days. This tiny world feels the full brunt of solar gravity, experiencing gravitational acceleration nearly 7 times stronger than what Earth encounters. Venus moves more leisurely at 35 kilometers per second, taking 225 days to finish each circuit. Our home planet maintains a comfortable 29 kilometers per second, neither rushing nor dawdling through its annual journey. As we venture farther from the Sun, orbital velocities continue dropping in precisely the manner Kepler's laws predict. Mars trudges along at 24 kilometers per second, while Jupiter manages only 13 kilometers per second despite its enormous mass. Saturn, Uranus, and Neptune progressively slow down as distance weakens the solar gravitational grip that holds them in orbit. Neptune, our most distant major planet, barely manages 5 kilometers per second, taking 165 Earth years to complete a single lazy circuit around the Sun. This orderly progression from fast inner planets to slow outer worlds represents exactly what gravitational theory demands. The mathematical relationship underlying these patterns stems from Newton's inverse square law, which states that gravitational force decreases proportionally to 1 over the square of the distance between objects. Double the separation, and gravitational attraction drops by a factor of 4. Triple the distance, and the force becomes 9 times weaker. This rapid fall-off means that objects orbiting far from massive central bodies experience dramatically reduced gravitational acceleration, requiring much slower velocities to maintain stable circular paths. When astronomers first began studying galactic rotation during the early 20th century, they naturally expected to find similar patterns operating on cosmic scales. Galaxies should behave like enormous solar systems, with stars near the center racing through their orbits, while those at the edges moved much more slowly. The visible matter in most galaxies concentrates heavily towards central regions, creating gravitational conditions that should produce steep velocity gradients exactly analogous to what we observe among planets. Mathematical models based on Newtonian mechanics painted a clear picture of how galactic rotation curves should appear. Stars within the bright central bulge would orbit at maximum velocities, typically reaching several hundred kilometers per second. Moving outward through the galactic disk, stellar velocities should decline steadily, according to the same inverse square relationship that governs planetary motion. By the time astronomers reached the visible edges of galactic disks, they expected to find stars crawling along at speeds perhaps 1/3 or 1/4 of the central values. The predicted rotation curves resembled ski slopes, starting high at galactic centers and falling off smoothly toward the outer reaches where starlight faded into darkness. This represents precisely what observations should reveal if galaxies contain only the matter we can directly detect through telescopes. The luminous stars, glowing gas clouds, and scattered dust particles that make up the visible components of galactic disks should provide all the gravitational binding necessary to explain stellar orbital motions throughout these systems. Yet when sensitive instruments finally became available to measure stellar velocities across entire galactic disks, astronomers discovered something that shattered their theoretical expectations. Instead of the predicted declining rotation curves, they found flat velocity profiles that maintained nearly constant values from galactic centers all the way out to the limits of detection. Stars at the edges of visible disks moved just as fast as those near the bright central bulges, completely violating the gravitational relationships that govern every other rotating system in the known universe. This cosmic merry-go-round seemed to operate under entirely different physical laws, as if the fundamental forces of nature somehow changed their behavior when a applied to galactic scales rather than planetary ones. How did one determine astronomers' meticulous observations in the 1970s revolutionize our understanding of cosmic architecture and reveal that 95% of the universe consists of completely unknown forms of matter and energy? Vera Rubin began her career during an era when many institutions still refused to admit women into their graduate programs, forcing her to pursue astronomy through sheer persistence and exceptional talent that could not be ignored. By the mid-1970s, she had gained access to sensitive spectrographic equipment at Kitt Peak National Observatory, instruments capable of detecting the faint light from individual gas clouds within distant spiral galaxies. Rubin focused her attention on measuring rotation velocities throughout galactic disks, using the 21-centimeter hydrogen emission line, a spectral signature that reveals the motion of neutral atomic hydrogen through precise Doppler shift measurements. Her systematic survey of nearby spiral galaxies represented the first comprehensive attempt to map stellar and gas velocities from bright central regions all the way out to the dim edges where starlight fades into cosmic darkness. What she discovered would fundamentally transform astronomy and cosmology, revealing evidence for invisible matter that outweighs everything we can see by factors of 5 to 1. The galaxy NGC 3198 became the poster child for this cosmic revolution, a textbook example of how galactic rotation curves violate every expectation based on visible matter distributions. Located roughly 45 million light-years from Earth in the constellation Ursa Major, NGC 3198 appears as a classic spiral galaxy, with sweeping arms and a bright central bulge containing most of its observable stellar population. When Rubin measured gas velocities throughout this system, she expected to find the declining rotation curve that Newtonian mechanics demanded. Instead, her data revealed something impossible according to established physics. Stars and gas clouds near the galactic center race through their orbits at velocities approaching 150 kilometers per second, exactly as theoretical models predicted. But rather than slowing down at greater distances from the center, these velocities remained essentially constant all the way out to the limits of her measurements. Gas clouds located 40,000 light-years from the galactic nucleus moved just as fast as those only 5,000 light-years away, completely ignoring the gravitational relationships that should govern their motion. The implications staggered scientific imagination. According to Newton's laws, maintaining such flat velocity profiles required the presence of additional gravitating matter distributed throughout galactic halos in precisely the right proportions to offset the natural tendency for rotation curves to decline. The visible stars provided only a small fraction of the total gravitational influence needed to explain the observed stellar motions. Rubin's calculations indicated that NGC 3198 contained at least 5 times more mass than could be accounted for by all the observable stars, gas, and dust within the galactic disk. Initially, many astronomers suspected systematic errors in these revolutionary measurements. Perhaps interstellar extinction was dimming distant stars more than expected, or maybe complex gravitational interactions between spiral arms created velocity perturbations that mimic the signatures of additional matter. But as Rubin extended her survey to include dozens of additional spiral galaxies, the same flat rotation curves appeared with monotonous regularity. Galaxy after galaxy revealed identical violations of gravitational expectations, suggesting that this phenomenon represented a universal feature of galactic architecture rather than an isolated anomaly. The Andromeda Galaxy, our nearest major galactic neighbour, showed flat rotation curves extending far beyond its visible stellar disk. The Whirlpool Galaxy, famous for its spectacular spiral structure, exhibited the same mysterious velocity patterns. Even edge-on systems where dust lanes obscured direct optical observations revealed flat rotation curves when studied through radio telescope measurements of neutral hydrogen emission. Every spiral galaxy examined through sufficiently sensitive instruments displayed evidence for enormous quantities of invisible matter extending far beyond the regions where stars could be detected. These observations forced astronomers to confront an uncomfortable truth. Either the fundamental laws of physics broke down completely on galactic scales, or the universe contained vast amounts of matter that interacted with ordinary material only through gravitational attraction. The second possibility required acceptance of a new category of cosmic constituent that remained completely invisible to electromagnetic radiation: particles that could neither emit light nor absorb it yet nonetheless shaped galactics, evolution through their gravitational influence. This dark matter hypothesis explained not only the flat rotation curves, but also provided a framework for understanding how galaxies formed in the first place, creating gravitational wells that attracted ordinary matter and enabled star formation throughout cosmic history. What happens when you realize that everything visible in the universe represents merely the tip of an iceberg whose hidden bulk extends across distances so vast they challenge human comprehension itself? Modern radio telescopes equipped with exquisitely sensitive receivers can detect the faint 21-centimeter emission from neutral hydrogen gas, extending far beyond the regions where optical telescopes find any trace of starlight, revealing that galactic rotation curves maintain their flat profiles out to distances exceeding 200 kiloparsecs from central regions. To appreciate this scale, consider that our entire Milky Way galaxy spans roughly 100 kiloparsecs from edge to edge, meaning these mysterious velocity patterns persist across volumes large enough to contain multiple complete galactic systems. The invisible architecture responsible for maintaining flat rotation curves extends 10 to 100 times farther into space than the visible components of galaxies themselves, creating spherical zones of gravitational influence that dwarf the stellar disks they surround. Picture trying to map the foundation of a skyscraper and discovering that its underground supports stretch across an entire city block, extending dozens of stories below street level to anchor a structure that appears modest when viewed from above. This analogy barely captures the proportional relationship between visible galactic matter and the dark scaffolding that holds it together through gravitational attraction. Within these enormous spherical halos, invisible matter particles follow complex orbital patterns that maintain the precise mass distributions required to produce flat rotation curves throughout galactic disks. Computer simulations suggest that dark matter halos contain intricate substructure, with smaller clumps and filaments creating a cosmic web that guides the formation and evolution of visible structures over billions of years. The largest dark matter halos associated with massive elliptical galaxies can extend across volumes containing enough space to fit 50 complete Milky Way systems, yet these vast regions remain completely invisible to every electromagnetic detector humans have constructed. Even more remarkable, gravitational lensing studies reveal that these invisible structures maintain their coherence and stability across cosmic timescales that span significant fractions of the universe's total age. Galaxy clusters observed at distances corresponding to look-back times of several billion years show the same lensing signatures that indicate massive dark matter concentrations, suggesting that this invisible scaffolding established itself during the early epochs of cosmic evolution and has persisted essentially unchanged ever since. The dark matter halos surrounding individual galaxies represent just one level of an hierarchical structure that extends across multiple scales simultaneously. Groups and clusters of galaxies sit embedded within even larger dark matter concentrations that can span tens of millions of light years, creating gravitational frameworks that bind hundreds or thousands of individual galactic systems into stable associations. These cluster-scale dark matter halos contain total masses equivalent to quadrillions of solar masses, yet they remain as invisible as the smaller structures that surround individual galaxies like our own Milky Way. The persistence of these vast invisible architectures across billions of years of cosmic evolution suggests fundamental stability in whatever physical processes govern dark matter behavior. Unlike ordinary matter, which can lose energy through electromagnetic radiation and collapse into compact configurations, dark matter appears immune to such dissipative effects. This property allows dark matter structures to maintain their extended configurations indefinitely, providing stable gravitational environments within which ordinary matter can condense into stars and planets over cosmic time. The implications become even more profound when you consider that dark matter halos began forming during the earliest epochs of cosmic history, long before the first stars ignited nuclear fusion in their cores. These invisible structures created the gravitational wells that attracted primordial hydrogen and helium, enabling the formation of the first stellar populations that enriched interstellar space with heavier elements necessary for planet formation and ultimately biological evolution. Without this invisible cosmic scaffolding, the universe would contain nothing but a nearly uniform distribution of gas, gradually cooling toward her absolute zero temperature devoid of the complex structures that make galaxies, stars, planets, and life itself possible. Every atom in your body once resided within one of these vast dark matter halos, drawn together by gravitational forces operating across scales ranging from individual particles to cosmic superclusters. The calcium in your bones, the iron in your blood, and the carbon in your DNA all trace their origins to stellar nucleosynthesis processes that occurred within galaxies held together by invisible matter extending across distances measured in hundreds of thousands of light years, persistent across time spans exceeding 10 billion years of cosmic evolution. Could it be that everything humanity has ever observed through telescopes represents less than 5% of the matter that actually exists throughout the cosmos, while 26% consists of completely invisible particles that surround us at this very moment yet remain undetectable to our senses? The story of discovering this hidden universe begins in 1933 with Swiss astronomer Fritz Zwicky, whose observations of the Coma cluster would fundamentally challenge our understanding of cosmic composition. Zwicky was studying the motions of individual galaxies within this massive collection of over 1,000 galactic systems located roughly 300 million light-years from Earth. Using the Mount Wilson Observatory's sophisticated spectrographs, he measured the Doppler shifts of light from galaxies scattered throughout the cluster, revealing their velocities as they orbited within the gravitational field created by the cluster's total mass. What Zwicky discovered violated every expectation about how such systems should behave according to established gravitational theory. The galaxies were moving far too quickly to remain gravitationally bound within the cluster, based solely on the mass contained in their visible stars. His calculations indicated that these galactic systems should have escaped into intergalactic space long ago unless something invisible but incredibly massive was providing additional gravitational binding to hold the entire structure together. Zwicky estimated that the cluster required roughly 10 times more matter than could be accounted for by all the observable stellar populations combined. He coined the term Dunkel materia, which translates as dark matter, to describe this mysterious missing mass that seemed to permeate the cluster while remaining completely invisible to electromagnetic detection. For decades after Zwicky's pioneering work, most astronomers dismissed his findings as observational errors or incomplete understanding of cluster dynamics. The idea that vast quantities of invisible matter could exist throughout the universe seemed too radical to accept without overwhelming evidence. But as observational techniques improved and similar discrepancies emerged from studies of individual galaxy rotation curves, the scientific community gradually recognized that Zwicky had identified a fundamental component of cosmic architecture. Modern cosmological observations have confirmed that ordinary matter, the atoms and molecules that comprise everything from stars to planets to living organisms, represents merely 5% of the universe's total mass energy content. Dark matter accounts for 26%, meaning that invisible particles outweigh everything we can see by a ratio of more than 5:1. For every proton, neutron, and electron that contributes to the familiar world of chemistry and biology, there exist roughly 5 particles of something entirely different that interacts with ordinary matter only through gravitational attraction. These dark matter particles appear to possess mass, but remain immune to electromagnetic forces, making them invisible to light while allowing them to clump together under their own gravity to form the cosmic scaffolding that shapes large-scale structure throughout the universe. The leading theoretical framework, known as cold dark matter or CDM, proposes that these mysterious constituents move relatively slowly compared to the speed of light and began clustering together during the earliest epochs of cosmic history. Unlike hot dark matter candidates such as neutrinos, which would have streamed freely through space and prevented small-scale structure formation, cold dark matter particles could have aggregated into gravitational wells that attracted ordinary matter and enabled the formation of the first stars and galaxies. Computer simulations based on CDM models successfully reproduce many observed features of cosmic structure, from the distribution of galaxy clusters down to the internal properties of individual galactic halos. However, alternative theories continue to compete for scientific acceptance. Warm dark matter models invoke particles with intermediate velocities that could resolve certain discrepancies between simulations and observations on small scales. Self-interacting dark matter theories propose that these invisible particles can collide with each other through forces other than gravity, potentially explaining why some galactic centers appear less dense than standard CDM predicts. Even more exotic possibilities include sterile neutrinos, axions, or entirely unknown categories of particles that might emerge from extensions to the standard model of particle physics. The profound implications of dark matter's existence extend far beyond academic cosmology. These invisible constituents shape the formation of every structure we observe, from the Milky Way galaxy that contains our solar system to the local group of galaxies within which we reside. Without dark matter providing gravitational anchoring points for ordinary matter to condense around, the universe would contain nothing but a nearly uniform distribution of hydrogen and helium gradually cooling toward absolute zero, devoid of stars, planets, or any possibility for complex chemistry and biological evolution. What would happen if you could strip away 99.99% of the visible matter from a galaxy while leaving its invisible scaffolding completely intact, creating a cosmic structure that exists almost entirely as gravitational architecture without substance? Dragonfly 44 represents exactly this impossible scenario, pushing the boundaries of dark matter domination so far beyond normal galactic compositions that it challenges our fundamental understanding of how such systems could possibly form or survive across billions of years of cosmic evolution. While typical galaxies contain roughly 10 to 15% visible matter in the form of stars, gas clouds, and cosmic dust, with the remaining 85 to 90% consisting of invisible dark matter particles, Dragonfly 44 exhibits proportions so extreme they seem to violate the basic principles governing galactic assembly throughout the universe. This ghostly structure contains only 1/100% ordinary matter, meaning that for every single atom of hydrogen, helium, carbon, or any other familiar element within its boundaries, there exist 10,000 invisible particles that contribute nothing to the galaxy's luminosity, yet provide virtually all of its gravitational binding energy. To comprehend the staggering implications of this composition, consider that our own Milky Way galaxy contains approximately 400 billion stars, vast molecular clouds spanning hundreds of light years, and countless planetary systems distributed throughout spiral arms that stretch across 100,000 light years of space. Yet even this enormous collection of visible matter represents only about 10% of our galaxy's total gravitational influence. The remaining 90% consists of dark matter particles that flow through interstellar space like invisible rivers, shaping stellar orbits and maintaining the spiral structure we observe while remaining completely undetectable to electromagnetic radiation across all wavelengths, from radio waves to gamma rays. Dragonfly 44 takes this hidden universe concept to previously unimaginable extremes, existing as what amounts to a cathedral constructed entirely from invisible materials, with just enough ordinary matter scattered throughout to catch starlight and reveal the presence of this vast gravitational edifice. The few billion stars within its boundaries serve essentially as luminous tracers, tiny beacons that mark the presence of underlying dark matter architecture spanning distances comparable to major galactic systems, yet containing stellar populations smaller than many globular clusters orbiting within the Milky Way's halo. This represents the most extreme example of dark matter domination ever discovered among galactic structures, surpassing even the previous record holders by factors of hundreds or thousands in terms of the ratio between invisible and visible components. The scientific implications extend far beyond simple record setting, because objects like Dragonfly 44 provide natural laboratories for studying dark matter behavior under conditions that cannot be replicated through any earthbound experiment or computer simulation. When dark matter comprises such overwhelming fractions of total mass, its gravitational effects become isolated from the complex feedback processes that ordinarily couple visible and invisible matter within galactic environments. Stellar winds, supernova explosions, and radiation pressure from massive stars typically influence both ordinary gas dynamics and dark matter distributions through gravitational interactions, creating intricate feedback loops that complicate attempts to understand pure dark matter physics. But Dragonfly 44 eliminates most of these complications by containing so few stars that their collective influence becomes negligible compared to the gravitational forces generated by invisible constituents. This allows astronomers to study dark matter halos in their pristine form, uncontaminated by the energetic processes associated with active star formation regions or nuclear activity from central supermassive black holes. The galaxy essentially functions as a dark matter physics laboratory where Theoretical predictions about particle behavior can be tested against observational reality without interference from electromagnetic phenomena. Furthermore, the extreme mass-to-light ratios observed in Dragonfly 44 place stringent constraints on alternative theories that attempt to explain galactic rotation curves through modifications to gravitational physics rather than invoking invisible matter. Modified Newtonian dynamics and similar approaches struggle to account for systems where visible matter provides such tiny fractions of the total gravitational influence, because these theories typically require some coupling between observable and dynamical mass that becomes increasingly difficult to maintain as dark matter fractions approach 100%. The existence of ultra-diffuse galaxies like Dragonfly 44 therefore serves as powerful evidence supporting particle-based explanations for cosmic structure rather than alternative gravitational frameworks, demonstrating that invisible matter must be a real physical constituent of the universe rather than merely an artifact of incomplete understanding about how gravity operates on cosmological scales. How can invisible matter organize itself into precise mathematical patterns that extend across hundreds of thousands of light years while maintaining structural coherence for billions of years without any electromagnetic forces to guide its architecture? The dark matter halo surrounding Dragonfly 44 follows what astrophysicists call the Navarro-Frank-White density profile, a specific mathematical relationship discovered through computer simulations of cosmic structure formation that describes how invisible particles arrange themselves within gravitational wells across the universe. Named after Julio Navarro, Carlos Frank, and Simon White, this NFW profile reveals that dark matter halos exhibit remarkably similar internal structures regardless of their total mass or formation history, suggesting fundamental physical principles govern the assembly of invisible cosmic scaffolding. The NFW formula predicts that dark matter density starts extremely high at the very center of galactic halos, then decreases according to a precise mathematical function that falls off more gradually than simple exponential decay, but faster than the inverse square law that governs planetary gravity. This creates what researchers describe as a cuspy central concentration surrounded by more diffuse outer regions that extend far beyond any visible galactic components. Computer simulations consistently reproduce this same density pattern across systems ranging from dwarf galaxy halos containing millions of solar masses to massive cluster environments weighing quadrillions of times more than our Sun. The spherical symmetry of dark matter halos contrasts dramatically with the flattened disk geometry that characterizes visible galactic components, creating a cosmic architecture where thin stellar disks float within vast spherical oceans of invisible particles. While ordinary matter can lose energy through electromagnetic radiation and collapse into compact configurations, dark matter appears immune to such dissipative processes, maintaining extended spherical distributions that preserve the memory of their initial formation conditions across cosmic time. This fundamental difference in behavior explains why visible and invisible matter organize themselves into completely different geometric arrangements despite sharing the same gravitational environment. The dark matter halo surrounding Dragonfly 44 extends roughly 10 times farther from the galactic center than the visible stellar distribution, creating a vast invisible reservoir that contains more than 99% of the system's total mass, while contributing nothing to its optical brightness. Within this enormous spherical volume, invisible particles follow complex orbital patterns that maintain the precise mass distribution required to produce flat rotation curves throughout the tiny visible disk floating at the halo center. Gravitational interactions between individual dark matter particles create a dynamic equilibrium that has persisted for billions of years, demonstrating remarkable stability in cosmic structures built entirely from components that remain undetectable to electromagnetic observation. One of the most intriguing aspects of Dragonfly 44 involves the population of globular clusters scattered throughout its outer regions, ancient stellar systems that formed during the galaxy's earliest evolutionary phases and now serve as tracers for mapping the underlying dark matter distribution. Initial observations suggested the presence of roughly 90 globular clusters, far more than expected for such a dim galactic system and potentially indicating formation within an extremely massive dark matter environment. However, subsequent detailed analysis using improved imaging techniques revised this number downward to approximately 20 clusters, still elevated compared to typical expectations, but no longer requiring the most extreme dark matter scenarios. These globular clusters orbit within the dark matter halo, like tiny islands of visible matter floating through an invisible ocean, their motions revealing the gravitational influence of particles that cannot be directly detected through any electromagnetic means. The revised globular cluster count has important implications for understanding how Dragonfly 44 formed and evolved, because these ancient stellar systems typically correlate with the total mass of their host dark matter, halos. Fewer clusters suggest a somewhat less massive halo than originally estimated, though still requiring enormous quantities of invisible matter to explain the observed stellar velocity dispersions. The entire structure resembles a vast cathedral constructed from invisible materials, with scattered candles representing the few visible stars and globular clusters that reveal the presence of this ghostly architecture through their faint light. The dark matter particles themselves remain as undetectable as the space between atoms, yet their collective gravitational influence shapes every aspect of galactic dynamics, from the smallest stellar orbits to the largest scale structural features. This invisible scaffolding provides the foundation upon which all visible cosmic architecture ultimately depends, creating stable environments where ordinary matter can condense into stars and planets across billions of years of cosmic evolution. What if the entire dark matter paradigm represents nothing more than an elaborate intellectual detour, and the real solution to galactic rotation mysteries lies not in populating space with invisible particles, but in recognizing that gravity itself operates differently than we assumed when applied across cosmic distances? In 1983, Israeli physicist Mordechai Milgrom proposed a revolutionary alternative to dark matter theory called modified Newtonian dynamics, universally abbreviated as MUND, which suggests that Newton's famous inverse square law breaks down when gravitational accelerations drop below a critical threshold of roughly 1/10,000,000th of Earth's surface gravity. According to Milgrom's framework, the familiar F equals ma relationship that governs motion in terrestrial environments transitions to a different mathematical form under conditions of extremely weak acceleration, such as those experienced by stars orbiting in the outer regions of galactic disks where rotation curve anomalies first appear. This seemingly modest adjustment to fundamental physics eliminates the need for vast quantities of invisible matter by allowing gravity to maintain stronger influence over larger distances than classical theory predicts, naturally producing the flat rotation curves that initially motivated dark matter hypotheses. Mond achieves remarkable success in predicting the detailed shapes of rotation curves across hundreds of different spiral galaxies, often matching observational data with greater precision than dark matter models that require careful fine-tuning of halo properties to reproduce the same results. The theory's most compelling feature lies in its ability to connect galactic dynamics directly to the distribution of visible matter, establishing tight correlations between stellar populations and rotation velocities that seem almost magical compared to the complex relationships required by dark matter scenarios. Milgrom discovered that a single universal acceleration scale, approximately 1.2 times 10^2, the minus 10 meters per second squared, governs the transition between Newtonian and modified regimes across all galactic systems regardless of their size, mass, or morphological classification. This fundamental constant appears repeatedly throughout astronomical observations, suggesting that it represents a genuine feature of gravitational physics rather than a coincidental numerical artifact. Mond advocates argue that requiring vast quantities of exotic particles to explain galactic dynamics violates Occam's razor, the philosophical principle that simpler explanations should be preferred when they adequately account for observational evidence. Instead of invoking entirely new categories of matter, with properties specifically designed to solve rotation curve problems, Moenda modifies our understanding of gravity itself through minimal changes to established physical laws, preserving the essential structure of Newtonian mechanics while extending its applicability to previously unexplored regimes of extremely weak acceleration. The theory successfully predicts many galactic phenomena that dark matter models struggle to explain, including the remarkable correlation between rotation curve shapes and surface brightness profiles known as the Tully-Fisher relation, which connects galactic luminosity to rotational velocity through relationships that Mond derives naturally from first principles. However, MOND faces significant challenges when applied to larger cosmic structures beyond individual galaxies. Galaxy cluster dynamics, where dozens or hundreds of massive galactic systems orbit within enormous gravitational wells, require much more exotic modifications to gravity than the simple acceleration threshold that works so well for isolated spiral galaxies. The famous Bullet Cluster, consisting of two galaxy clusters that collided and passed through each other roughly 150 million years ago, presents particularly difficult problems for MOND because gravitational. Lensing observations reveal that most of the system's mass appears spatially separated from the visible matter that presumably generates the gravitational field. Dark matter models explain this phenomenon elegantly by proposing that invisible particles pass through the collision without interacting, while ordinary matter experienced drag forces that slowed its progress. But MOND requires increasingly complex gravitational modifications to account for the same observational evidence. Furthermore, cosmological observations of the cosmic microwave background radiation, large-scale structure formation, and primordial nucleosynthesis all point toward the existence of non-baryonic matter, with properties that match dark matter predictions remarkably well, creating a web of independent evidence that extends far beyond galactic rotation curves. MOND proponents continue developing relativistic extensions of the theory that might address these larger-scale challenges, but each modification introduces additional complexity that undermines the original appeal of Occam's razor arguments. The ongoing debate between dark matter and modified gravity represents one of the most fundamental controversies in modern physics, touching on questions about the nature of space-time, the completeness of our understanding about gravitational interactions, and whether the universe contains exotic forms of matter that interact with ordinary particles only through gravitational forces. What happens when the most celebrated discovery in dark matter research becomes the center of a bitter scientific controversy that divides the astronomical community into opposing camps, with fundamentally different interpretations of the same observational data? In 2018, Peter van Dokkum and his research team published revised measurements of Dragonfly 44 that dramatically reduced their estimates of the galaxy's total mass from 1 trillion solar masses down to approximately 160 billion solar masses, a six-fold decrease that fundamentally altered the implications of their groundbreaking discovery. This massive revision emerged from improved spectroscopic observations using the Keck Cosmic Web Imager, which provided higher spatial resolution and longer integration times than the original measurements that had established Dragonfly 44 as the most extreme example of dark matter domination ever found among galactic structures throughout the cosmos. The new velocity dispersion measurements yielded values of 33 km per second rather than the 47 km per second reported in their initial analysis, a seemingly modest change that translated into enormous differences in calculated gravitational mass due to the square dependence of dynamical mass estimates on stellar velocity measurements. Simultaneously, independent research groups began questioning the globular cluster counts that had provided supporting evidence for Dragonfly 44's extreme mass estimates, with some teams reporting significantly fewer ancient stellar systems than the 90 clusters originally identified through ground-based telescopic observations. Using data from the Hubble Space Telescope and advanced image processing techniques, these alternative analyses suggested that many objects initially classified as globular clusters were actually background galaxies or imaging artifacts created by the challenging observational conditions required to study such faint galactic structures. Aaron Romanowski and his collaborators published competing measurements indicating that Dragonfly 44 contained closer to 20 globular clusters, a number more consistent with lower mass estimates and potentially undermining claims about the galaxy's unprecedented dark matter content. The revised measurements provided ammunition for proponents of modified Newtonian dynamics, with Stacey McGaw of Case Western Reserve University arguing that the new data vindicated MOND predictions about galactic rotation curves and eliminated the need for exotic dark matter explanations. McGaw pointed out that MON naturally predicted rotation velocities consistent with the revised stellar velocity dispersions, while the original extreme measurements had required dark matter scenarios that pushed theoretical models beyond their established limits of applicability. He claimed that Dragonfly 44 represented another example of how initial observational errors had been misinterpreted as evidence for dark matter, following a pattern he argued was repeated throughout the history of the galactic dynamics research, where improved measurements consistently reduced the apparent need for invisible matter. However, Van Dockum vigorously defended his team's dark matter interpretation, even with the revised mass estimates, arguing that a galaxy containing 160 billion solar masses, while producing only 1% of the Milky Way's luminosity, still required extraordinary amounts of invisible matter to maintain structural stability. The reduced mass estimates merely changed a Dragonfly 44 from the most extreme example of dark matter domination to a somewhat less extreme but still remarkable case study in cosmic structure formation, preserving the fundamental conclusion that this galactic system consisted primarily of particles that interact only through gravitational forces. Van Dockum emphasized that the revised measurements maintained mass-to-light ratios approximately 6 times higher than normal galaxies exhibit, indicating that dark matter still comprised roughly 85% of the system's total gravitational mass, even under the most conservative interpretations of the observational evidence. The controversy highlighted fundamental challenges facing astronomical research when dealing with objects at the limits of current observational capabilities, where systematic errors and selection effects can significantly influence scientific conclusions about the nature of cosmic architecture. Different research groups using different telescopes, instruments, and analysis techniques continued producing conflicting measurements of basic properties like stellar velocity dispersions and globular cluster populations, making it difficult to establish definitive conclusions about Dragonfly 44's mass and dark matter content. The debate also revealed deeper philosophical divisions within the astronomical community about the burden of proof required to establish extraordinary claims, with some researchers arguing that exceptional evidence was needed to support dark matter scenarios, while others maintained that standard observational techniques provided sufficient validation for invisible matter hypotheses. These ongoing controversies demonstrate how scientific progress often involves prolonged periods of uncertainty and disagreement before consensus emerges around competing theoretical frameworks, especially when dealing with phenomena that challenge established understanding about fundamental physical processes governing cosmic evolution. What if dark matter consists not of heavy particles behaving like cosmic bullets, but rather of ultralight quantum entities that exist in superposition states spanning entire galactic systems and create interference patterns visible only through their gravitational effects on stellar motion? Among the most intriguing alternatives to conventional cold dark matter models, fuzzy dark matter proposes that invisible cosmic constituents might be actions or similar ultralight particles with masses billions of times smaller than electrons, so ethereal that their quantum mechanical properties become relevant across astronomical distances rather than being confined to subatomic scales. These hypothetical particles would exhibit wave-like behavior on kiloparsec length scales, creating quantum interference effects that could explain why some galactic cores appear less dense than traditional dark matter simulations predict, while simultaneously accounting for the large-scale structure formation patterns observed throughout cosmic history. The wave nature of ultralight dark matter creates natural length scales below which gravitational clumping becomes suppressed by quantum pressure, potentially resolving discrepancies between simulated and observed properties of dwarf galaxies that have troubled conventional dark matter scenarios for decades. When billions of these quantum particles occupy the same gravitational well, they form what physicists call a Bose-Einstein condensate, a macroscopic quantum system where individual particle identities become indistinguishable, and the entire collection behaves as a single coherent wave function spanning galactic dimensions. This quantum condensate exhibits properties fundamentally different from classical particle distributions, including the ability to support standing wave patterns that create density oscillations throughout galactic halos, potentially explaining observed correlations between stellar and dark matter distributions that seem mysteriously fine-tuned in standard scenarios. Even more exotic possibilities emerge from superfluid dark matter theories, which propose that invisible particles can undergo phase transitions under certain temperature and density conditions, flowing through galactic environments without friction, while maintaining perfect rotational motion that naturally produces flat velocity curves without requiring carefully arranged density profiles. These superfluid phases might explain why galactic rotation curves exhibit such remarkable uniformity across different systems, because the underlying quantum fluid mechanics would impose universal relationships between mass distributions and rotational velocities regardless of individual formation histories or environmental influences. Self-interacting dark matter models represent another radical departure from conventional wisdom by proposing that invisible particles can collide with each other through forces other than gravity, allowing them to exchange momentum and thermalize within galactic cores over cosmic timescales. These interactions could soften the cuspy central density profiles predicted by collisionless dark matter simulations, creating more spherical core regions that better match observations of dwarf galaxies and low-surface brightness systems like Dragonfly 44. The strength of self-interactions required to produce observable effects must be carefully calibrated to avoid disrupting larger-scale structure formation while still influencing galactic cores, suggesting that dark matter might possess a rich spectrum of physical properties rather than the minimal characteristics assumed by standard cold dark matter frameworks. Mirror matter theories propose an even more radical possibility, that dark matter consists of ordinary atoms and molecules existing in a parallel sector of physics that interacts with our familiar matter only through gravitational attraction. This hidden sector could contain mirror stars, mirror planets, and even mirror life forms that remain completely invisible because they emit and absorb photons from a separate electromagnetic field that does not couple to the particles comprising ordinary matter. While mirror matter scenarios can explain the apparent absence of electromagnetic interactions with dark matter, they struggle to account for the precise cosmological properties required for successful structure formation and must invoke additional mechanisms to prevent mirror sector cooling that would create overly dense galactic cores. Sterile neutrino models offer yet another approach by proposing that dark matter consists of additional neutrino species that do not participate in weak nuclear interactions, making them even more elusive than the standard neutrinos already known to exist in vast numbers throughout the universe. These sterile neutrinos could be produced through quantum oscillations with ordinary neutrinos or through exotic decay processes in the early universe, potentially explaining both dark matter abundance and certain anomalous results from neutrino detection experiments. Perhaps most intriguingly, some theoretical physicists have begun questioning whether dark matter represents a genuine physical constituent at all, instead suggesting that apparent gravitational anomalies might result from emergent phenomena arising from quantum vacuum fluctuations or holographic information processing occurring at cosmic horizons. These approaches attempt to derive effective dark matter behavior from fundamental quantum field theory without requiring new particles, proposing that space-time itself might possess computational properties that create apparent mass-energy distributions through information processing mechanisms operating across cosmological scales. How does the universe construct galactic structures so fundamentally impossible that their very existence challenges every theoretical framework we have developed to explain cosmic evolution across 13.8 billion years of history? According to standard galaxy formation theory, cosmic architecture emerges through a hierarchical process that begins with tiny quantum fluctuations in the primordial universe, density variations so minute they barely registered above the smooth background of matter and energy that filled space during the earliest epochs following the Big Bang. These microscopic irregularities grew under their own gravitational attraction as the universe expanded and cooled, eventually becoming the seeds from which all large-scale structures would eventually emerge through processes that should produce nothing remotely resembling the extreme properties observed in Dragonfly 44. The conventional formation scenario starts with dark matter particles clumping together into increasingly massive concentrations called halos, invisible gravitational, wells that attract ordinary matter through their inexorable pull across millions of years of cosmic evolution. As hydrogen and helium gas falls into these dark matter scaffolds, it heats up through gravitational compression until temperatures become sufficient to ignite nuclear fusion reactions that give birth to the first generation of stars. Subsequent stellar evolution enriches the interstellar medium with heavier elements necessary for planet formation and complex chemistry, while supernova explosions and stellar winds regulate further star formation through feedback processes that prevent galaxies from converting all their gas into stars too rapidly. This bottom-up assembly process should naturally produce galaxy populations with specific relationships between their stellar masses, gas content, and underlying dark matter halo properties that reflect the universal physics governing structure formation throughout cosmic history. Computer simulations based on these principles successfully reproduce many observed characteristics of typical spiral and elliptical galaxies, including their size distributions, color patterns, and spatial clustering properties across different cosmic epochs. However, ultra-diffuse galaxies like Dragonfly 44 fall completely outside the parameter ranges that standard formation models can explain, possessing combinations of low stellar density and high dark matter content that seem impossible to achieve through any known evolutionary pathway. One proposed explanation involves the failed Milky Way hypothesis, which suggests that Dragonfly 44 represents a galaxy that began forming within an extremely massive dark matter halo, similar to those hosting large spiral systems, but somehow failed to convert its gas reservoir into stars at the expected rate. Perhaps feedback from the first generation of massive stars was so violent that it ejected most of the available fuel for subsequent star formation, leaving behind a dark matter halo, populated by only a tiny fraction of the stellar population it should contain based on its gravitational mass. This scenario requires exceptionally efficient stellar feedback mechanisms operating during the galaxy's early evolutionary phases, possibly involving coordinated supernova explosions or energetic outflows from a central supermassive black hole that could strip away the majority of baryonic matter while preserving the underlying dark matter structure. Alternative formation pathways invoke high-spin merger scenarios where two smaller galaxies collided while rotating in the same direction, creating a combined system with enough angular momentum to inflate its stellar distribution across much larger volumes than typical galaxy formation processes would allow. The resulting structure might retain the total dark matter content from both progenitor systems, while spreading its stellar population so thinly that surface brightness drops below normal detection thresholds, creating the ghostly appearance characteristic of ultra-diffuse galaxies. High-resolution numerical simulations suggest that such mergers could occur under specific initial conditions involving gas-rich dwarf galaxies with precisely matched orbital parameters, though the required configurations appear extremely rare in cosmological contexts. Environmental effects within dense galaxy clusters provide another possible formation mechanism through tidal stripping processes that selectively remove different galactic components based on their gravitational binding energies. As galaxies fall toward cluster centers, they experience increasingly strong tidal forces from the collective gravitational field created by hundreds of neighboring systems, plus the cluster's own dark matter halo. These tidal interactions can strip away loosely bound gas and outer stellar populations, while leaving more tightly bound components intact, potentially creating objects with unusual mass-to-light ratios. However, explaining Dragonfly 44's extreme properties require stripping mechanisms so efficient they remove 99% of the original stellar population while preserving the dark matter halo essentially unchanged, a level of selective disruption that seems difficult to achieve through gravitational forces alone. Why has the discovery of over 1,000 ultra-diffuse galaxies transformed our understanding of cosmic architecture from a relatively simple story about standard formation processes into a bewildering menagerie of impossible objects that each violate different aspects of theoretical expectations? Since the pioneering work that first identified Dragonfly 44 and its companions within the Coma cluster, systematic surveys using improved observational techniques have revealed these ghostly structures throughout the observable universe, from nearby galaxy groups to distant clusters containing hundreds of member systems. Each newly discovered ultra-diffuse galaxy adds another piece to a cosmic puzzle that grows more perplexing with every observation, because these objects exhibit such enormous diversity in their properties that no single formation mechanism appears capable of explaining the entire population through unified physical processes. Some ultra-diffuse galaxies contain substantial dark matter halos comparable to those found around normal spiral systems, while others appear almost completely devoid of invisible matter, creating a spectrum of dark matter fractions that spans the entire range from 0 to nearly 100%. This diversity challenges theoretical models that predict relatively narrow ranges of acceptable properties based on universal physics governing structure formation throughout cosmic history. Perhaps the most shocking members of this cosmic zoo are NGC 1052-DF2 and its companion NGC 1052-DF4, ultra-diffuse galaxies located roughly 65 million light-years from Earth that appear to contain little or no dark matter whatsoever. Despite their extended size and low stellar density, these systems exhibit stellar velocity dispersion so low that their total gravitational masses appear consistent with just the visible matter contained in their sparse stellar populations, completely eliminating the need for invisible particle halos that supposedly provide the gravitational scaffolding for all galactic structures. The existence of dark matter deficient galaxies creates profound challenges for lambda CDM cosmology, because standard formation theory predicts that all galaxies should assemble within pre-existing dark matter halos that provide the initial gravitational seeds for attracting ordinary matter. Somehow, NGC 1052, DF2, and DF4 managed to form extensive stellar systems without the invisible architectural framework that theoretical models require for galaxy assembly, suggesting unknown formation pathways that bypass conventional structure formation mechanisms entirely. Subsequent observations have revealed additional dark matter, poor ultra-diffuse galaxies in various environments, indicating that these anomalous objects represent more than isolated exceptions to standard formation paradigms. The diversity extends beyond simple dark matter content to include variations in stellar populations, globular cluster abundances, morphological structures, and environmental contexts that create what amounts to a cosmic laboratory for testing competing theories about galactic evolution. Some ultra-diffuse galaxies contain ancient stellar populations characteristic of early universe formation epochs, while others show evidence for more recent star formation activity that suggests ongoing evolution rather than fossil remnants from primordial times. Globular cluster populations vary dramatically among different systems, with some hosting hundreds of these ancient stellar associations, while others contain none whatsoever, creating additional constraints on formation scenarios that must explain how environmental conditions influence the assembly of gravitationally bound stellar groups. Environmental studies reveal that ultra-diffuse galaxies exist across diverse cosmic contexts, from dense cluster cores where tidal stripping processes operate most efficiently, to isolated field environments where such disruptive mechanisms should be negligible. This wide distribution suggests that multiple formation pathways contribute to the ultra-diffuse galaxy population, rather than a single dominant process operating under specific environmental conditions. Some systems appear to be genuine field galaxies that formed in relative isolation, while others show clear signatures of environmental processing through interactions with neighbouring systems or cluster-scale gravitational fields. The morphological diversity includes objects ranging from perfectly spherical distributions resembling giant elliptical galaxies to highly flattened disk systems that retain clear spiral structure despite their anomalously low surface brightness. These variations in shape and internal structure provide additional clues about formation mechanisms, because different assembly processes should produce characteristic morphological signatures that persist across cosmic timescales. Spectroscopic studies of individual ultra-diffuse galaxies reveal chemical abundance patterns that vary significantly among different systems, with some showing metal enrichment levels comparable to normal galaxies, while others exhibit the pristine compositions expected from systems with minimal star formation histories. Each discovery adds new parameters to the growing list of properties that successful formation theories must simultaneously explain, creating increasingly complex constraints that challenge our fundamental understanding of how cosmic structures assemble and evolve throughout universal history. Could it be that our most sophisticated computer simulations, which successfully model cosmic evolution across billions of years using millions of processors working in parallel, fundamentally misunderstand the basic physics governing how galaxies like Dragonfly 44 actually form and evolve throughout cosmic history? The Millennium Simulation, launched in 2005 as one of the largest computational projects ever undertaken in astrophysics, tracked the gravitational interactions of more than 10 billion dark matter particles across a cubic volume spanning 500 million light-years on each side, revealing how cosmic structure emerges from tiny initial fluctuations through 13 billion years of hierarchical assembly. This massive calculation required months of continuous operation on supercomputers containing thousands of processors, generating terabytes of data about how dark matter halos merge, grow, and acquire the satellite systems that eventually become the galaxies we observe today. Subsequent simulations have incorporated increasingly sophisticated physics, including gas dynamics, stellar feedback, supernova explosions, and black hole accretion to create virtual universes that reproduce many observed properties of galactic populations across different cosmic epochs. However, these computational triumphs consistently fail to predict the existence or properties of ultra-diffuse galaxies, producing synthetic galaxy catalogues that contain virtually no objects resembling the extreme systems discovered through observational surveys over the past decade. The discrepancies extend far beyond simple numerical differences to fundamental qualitative failures that suggest missing physics or incorrect assumptions about the processes governing galactic assembly throughout cosmic time. Standard cold dark matter simulations predict that dark matter halos should contain much larger numbers of luminous satellite galaxies than observations actually reveal, creating what researchers call the missing satellite problem that has persisted despite decades of increasingly sophisticated modelling efforts. Theoretical calculations indicate that massive halos like those hosting the Milky Way should harbour hundreds of smaller subhalos capable of forming dwarf galaxies, yet astronomical surveys identify fewer than 50 such systems within our local group environment. This factor of 10 discrepancy suggests either that most small halos fail to acquire stellar populations through unknown suppression mechanisms, or that simulation predictions overestimate the abundance of low-mass dark matter structures. Ultra-diffuse galaxies compound this puzzle by demonstrating that substantial stellar systems can form within dark matter halos while maintaining extremely low surface brightness, challenging models that connect stellar mass to halo mass through simple relationships. The core versus cusp controversy represents another persistent failure of numerical simulations to match observational reality, because computed dark matter density profiles consistently produce steep central cusps that concentrate most halo mass within inner regions, while observations of dwarf galaxies and low-surface brightness systems suggest flatter core structures with more uniform density distributions. Dragonfly 44 and similar objects provide crucial tests of this theoretical prediction, because their extreme dark matter fractions should preserve pristine signatures of halo structure without contamination from complex baryonic physics that complicates interpretation in normal galaxies. However, preliminary analyses suggest that even these dark matter-dominated systems exhibit core-like profiles rather than the cuspy distributions that simulations invariably produce, indicating fundamental problems with either computational methods or underlying assumptions about dark matter particle properties. Recent attempts to address these discrepancies have focused on incorporating more realistic stellar feedback mechanisms that can redistribute matter through energetic outflows driven by supernova explosions and stellar winds, potentially explaining both the missing satellite problem and the core cusp controversy through unified physical processes. These enhanced simulations suggest that repeated episodes of star formation and gas expulsion can gradually transform cuspy halo profiles into flatter core structures, while simultaneously preventing star formation in smaller subhalos that would otherwise produce observable dwarf galaxies. However, the feedback mechanisms required to explain these effects must operate with extraordinary efficiency, removing more than 90% of available gas from galactic environments while preserving the stellar populations that make galaxies detectable in the first place. The energy budgets involved in such dramatic transformations push stellar feedback models beyond their established limits, requiring supernova rates or coupling efficiencies that exceed what direct observations of star-forming regions actually support. Furthermore, feedback-based solutions struggle to explain the diversity observed among ultra-diffuse galaxy populations, because the same physical processes should produce relatively uniform outcomes rather than the wide range of dark matter fractions and structural properties that characterizes these enigmatic systems. The persistent failures of computational cosmology to predict or explain ultra-diffuse galaxies highlight fundamental gaps in our understanding of galactic physics that may require entirely new theoretical frameworks rather than incremental improvements to existing simulation techniques. What if the extreme properties exhibited by Dragonfly 40 and similar ultra-diffuse galaxies represent the first observable cracks in lambda CDM cosmology, the theoretical framework that has successfully explained everything from cosmic microwave background patterns to supernovae observations, but may be fundamentally incomplete when confronted with these impossible galactic structures? The lambda CDM model, named for the cosmological constant lambda that drives cosmic acceleration and cold dark matter that provides gravitational scaffolding for structure formation, represents the culmination of nearly a century of observational discoveries and theoretical advances that transformed our understanding of universal evolution from a static cosmos to a dynamic system expanding and cooling across 13.8 billion years of cosmic history. This standard model successfully predicts the precise temperature fluctuations observed in cosmic microwave background radiation, the fossil light from when the universe first became transparent roughly 380,000 years after the Big Bang, matching theoretical calculations to extraordinary precision across multiple angular scales and statistical measures. The same theoretical framework explains how tiny quantum fluctuations in the primordial universe grew into the vast web of galaxy clusters, filaments, and voids that characterize contemporary large-scale structure, connecting the smallest observable variations in early cosmic conditions to the largest architectural features spanning hundreds of millions of light-years. Lambda CDM models also account for the abundances of light elements produced during Big Bang nucleosynthesis, the observed relationship between galaxy distances and recession velocities known as Hubble's law, and the acceleration of cosmic expansion revealed through Type Ia supernova observations that earned the 2011 Nobel Prize in Physics. Yet despite these remarkable successes, extreme galaxies like Dragonfly 44 probe regimes of parameter space, where Lambda CDM predictions become increasingly uncertain, testing fundamental assumptions about dark matter properties and structure formation processes that may not hold under all cosmic conditions. The existence of galaxies with dark matter fractions approaching 100% provides natural laboratories for studying invisible matter behavior, without the complex feedback processes that typically couple ordinary and exotic matter through gravitational interactions mediated by stellar winds, supernova explosions, and radiation pressure from massive stars. These pristine dark matter systems should preserve the original signatures of halo assembly and evolution that occurred during early cosmic epochs, allowing direct comparison between theoretical predictions and observational reality without contamination from poorly understood baryonic physics that complicates interpretation in normal galactic environments. However, preliminary studies suggest that even these dark matter-dominated systems exhibit properties inconsistent with standard Lambda CDM expectations, including central density profiles that appear flatter than simulations predict and satellite populations that differ significantly from theoretical abundance patterns derived through hierarchical assembly models. The diversity observed among ultra-diffuse galaxy populations creates additional challenges for unified cosmological frameworks that should produce relatively narrow ranges of acceptable properties based on universal physics, governing structure formation throughout cosmic history. Some systems contain substantial amounts of invisible matter comparable to normal spiral galaxies, while others appear almost completely devoid of dark matter, despite their extended sizes and low stellar densities, creating a spectrum of compositions that spans the entire range from 0 to nearly 100% dark matter content. This extraordinary diversity suggests either that multiple formation pathways contribute to ultra-diffuse galaxy populations through processes not included in standard cosmological models, or that Lambda CDM itself contains fundamental misconceptions about how dark matter behaves under specific environmental conditions encountered during galactic assembly. The connection between small-scale galactic physics and large-scale cosmological models becomes particularly important because cosmic microwave background observations primarily constrain the total amount and general properties of dark matter across the entire observable universe, while galactic dynamics reveal how this invisible matter actually behaves within individual gravitational systems where nonlinear physics dominates evolutionary processes. Discrepancies between these different observational probes could indicate that dark matter exhibits more complex behavior than the simple collisionless particles assumed by standard models, potentially requiring modifications to fundamental assumptions about particle interactions or gravitational physics that would have profound implications for our understanding of cosmic evolution. The possibility that extreme galaxies like Dragonfly 44 represent harbingers of cosmological revolution recalls previous paradigm shifts when unexpected observations forced complete reconsideration of established theoretical frameworks, from the discovery of cosmic expansion that overturned static universe models to the detection of dark energy acceleration that required introduction of exotic components comprising 70% of universal mass energy content. How can humanity hope to detect particles so elusive they interact with ordinary matter only through gravity, requiring detection schemes so sensitive they must be shielded from cosmic radiation deep beneath mountain ranges while monitoring for collisions between invisible particles and atomic nuclei that occur perhaps once per year in tons of target material. The international race to directly detect dark matter particles has transformed abandoned mines and excavated caverns around the globe into sophisticated physics laboratories equipped with some of the most sensitive instruments ever constructed. Devices capable of registering individual particle interactions with energies comparable to a mosquito landing on your hand, yet occurring within detector volumes containing thousands of kilograms of ultra-pure materials maintained at temperatures approaching absolute zero. The large underground xenon experiment known as LUX operated nearly a mile beneath the Black Hills of South Dakota within the Samford Underground Research Facility, utilizing tanks filled with liquid xenon cooled to -100 degrees Celsius and surrounded by photomultiplier tubes sensitive enough to detect single photons produced when dark matter particles scatter off xenon nuclei through weak nuclear interactions. Despite years of continuous operation and exquisite sensitivity to particle interactions, LUX detected no convincing signals from dark matter collisions, establishing upper limits on interaction cross-sections that rule out many theoretical predictions about how invisible matter should couple to ordinary atoms through forces other than gravity. The Xenon collaboration has constructed even larger and more sensitive detectors using similar principles, but increased target masses and improved background rejection capabilities, pushing detection thresholds into previously unexplored regions of theoretical parameter space where exotic particles might reveal their presence through extremely rare collision events. Meanwhile, the Large Hadron Collider in Switzerland approaches dark matter detection from the opposite direction by attempting to create these mysterious particles through high-energy proton collisions that recreate conditions similar to those prevailing during the first microseconds after the Big Bang, when thermal energies were sufficient to produce all known particle species along with potentially unknown constituents that subsequently became the invisible scaffolding of cosmic architecture. These accelerator-based searches look for missing energy signatures in collision debris that would indicate the production and immediate escape of particles that interact too weakly with detector materials to leave direct traces, requiring sophisticated statistical analysis of millions of collision events to identify subtle patterns that might reveal dark matter creation through electromagnetic or weak nuclear processes. Indirect detection strategies focus on astronomical observations of high-energy radiation that might result from dark matter particle annihilation or decay within regions of exceptionally high invisible matter density, such as galactic centers or galaxy cluster cores, where dark matter concentrations reach their maximum values. Gamma-ray telescopes scan these targets, searching for spectral lines or continuum emission features that would indicate dark matter particles destroying each other to produce photons, electrons, or other standard model particles that subsequently create observable electromagnetic signals propagating across cosmic distances to Earth-based detectors. However, all these detection approaches face fundamental challenges when attempting to distinguish genuine dark matter signals from backgrounds created by ordinary astrophysical processes or instrumental artifacts, because the expected interaction rates remain so low that even single spurious events can contaminate years of accumulated data. This is where ultra-diffuse galaxies like Dragonfly 44 provide unprecedented opportunities for dark matter physics research by offering natural laboratories where invisible matter dominates gravitational dynamics without contamination from complex baronic processes that obscure dark matter signatures in normal galactic environments. The extreme dark matter fractions observed in these systems create gravitational fields produced almost entirely by invisible particles, allowing precision tests of dark matter theories without interference from stellar feedback, gas dynamics, or magnetic field effects that complicate interpretation in ordinary spiral galaxies. These clean dark matter environments enable direct comparison between theoretical predictions and observational measurements of phenomena like halo density profiles, substructure abundances, and velocity dispersion patterns that should reflect fundamental properties of dark matter, particle physics including mass, interaction cross-sections, and thermodynamic behavior under various density and temperature conditions. Furthermore, the diversity observed among ultra-diffuse galaxy populations provides multiple independent tests of dark matter models, because different formation scenarios should produce characteristic signatures in halo structure and satellite abundance that can discriminate between competing theoretical frameworks through systematic observational surveys. The combination of terrestrial detection experiments and astronomical observations of ultra-dark galaxies represents humanity's best strategy for finally identifying the nature of invisible matter that comprises 26% of universal mass energy, yet remains more mysterious than any other major component of cosmic architecture. What revolutionary discoveries await humanity as we deploy the most powerful observational instruments ever conceived, machines so sensitive they could detect the heat signature of a candle flame on the surface of the moon, while simultaneously mapping invisible matter distributions across billions of light-years of cosmic space? The James Webb Space Telescope, launched in late 2021 and now operating at the second Lagrange point beyond lunar orbit, represents a quantum leap in astronomical capability with its 6.5-meter segmented mirror and suite of infrared instruments designed to peer deeper into space and further back in cosmic time than any previous observatory. JWST's unprecedented sensitivity to infrared radiation enables detailed spectroscopic studies of ultra-diffuse galaxies at distances where previous telescopes could barely detect these ghostly structures, revealing their stellar populations, chemical compositions, and kinematic properties with precision that approaches what we can achieve for nearby systems within our local group. The telescope's ability to observe through cosmic dust that obscures visible light allows astronomers to study galaxy formation processes during the earliest epochs of universal history, potentially identifying primordial ultra-diffuse systems that formed when dark matter halos first began attracting ordinary matter during cosmic dawn. Even more ambitious capabilities will emerge from the Nancy Grace Roman Space Telescope, previously known as BOFIRST, which combines Hubble-class image quality with survey speeds hundreds of times faster than existing space-based observatories, enabling comprehensive mapping of weak gravitational lensing effects across unprecedented volumes of cosmic space. Roman's wide-field infrared camera will detect subtle distortions in background galaxy shapes caused by intervening dark matter concentrations, creating three-dimensional maps of invisible matter distribution that extend billions of light-years from Earth, while revealing how dark matter clustering evolves across cosmic time. These gravitational lensing surveys will provide direct measurements of dark matter properties within thousands of ultra-diffuse galaxies simultaneously, testing theoretical predictions about halo structure and substructure abundance through statistical analyses impossible with current observational capabilities. Ground-based astronomy is simultaneously undergoing revolutionary transformation through construction of extremely large telescopes with primary mirrors spanning 25 to 40 meters in diameter, collecting areas more than 10 times larger than today's largest optical observatories and spatial resolution approaching theoretical limits imposed by atmospheric turbulence. The European Extremely Large Telescope, 30-meter telescope, and Giant Magellan Telescope will achieve spectroscopic capabilities sufficient to measure individual stellar velocities within ultra-diffuse galaxies located hundreds of millions of light-years away, providing kinematic data comparable to what current 8-meter telescopes can obtain only for the nearest examples. Advanced adaptive optics systems using laser guide stars and deformable mirrors will correct atmospheric distortions in real time, delivering image quality that rivals space-based observations while maintaining the flexibility and upgradability advantages of ground-based facilities. These capabilities will enable detailed studies of globular cluster populations, stellar metallicity gradients, and internal structure within ultra-diffuse galaxies across cosmic distances, testing formation scenarios through observations of systems spanning wide ranges of environmental conditions and evolutionary stages. Perhaps most intriguingly, gravitational wave astronomy opens entirely new windows for studying dark matter through detection of space-time distortions created by merging black holes, neutron stars, and potentially exotic compact objects formed from invisible matter under extreme density conditions. The Laser Interferometer Gravitational Wave Observatory, along with its European counterpart Virgo and the planned space-based LISA mission, can potentially detect gravitational waves produced by dark matter phase transitions, primordial black hole mergers, or other exotic phenomena associated with invisible matter dynamics during early cosmic epochs. These gravitational signatures would provide completely independent confirmation of dark matter existence while revealing properties inaccessible through electromagnetic observations, potentially identifying the mass scale and interaction strength of dark matter particles through their influence on space-time curvature. future space-based gravitational wave detectors will achieve sensitivity levels capable of monitoring dark matter substructure mergers within galactic halos, providing direct dynamical measurements of invisible matter behavior that complement indirect inferences from stellar kinematics and gravitational lensing studies. The convergence of these multiple observational approaches represents humanity's most comprehensive assault on cosmic mysteries, combining electromagnetic radiation across all wavelengths with gravitational wave detection and particle physics to create a unified picture of universal architecture that includes both visible and invisible components. Within the next decade, these revolutionary instruments may finally resolve whether dark matter consists of exotic particles, modified gravitational physics, or phenomena beyond our current theoretical imagination, potentially answering questions about cosmic composition that have puzzled scientists since Fritz Zwicky first identified missing mass in galaxy clusters nearly a century ago. What does it mean for our fundamental understanding of existence itself when we discover that 95% of reality consists of forms of matter and energy, so alien to human experience that we cannot see them, touch them, or interact with them through any known mechanism except the invisible hand of gravity that shapes cosmic destiny across billions of light years? The revelation that dark matter and dark energy dominate universal composition forces us to confront the profound humility required when contemplating our place within a cosmos where everything familiar to human senses represents merely a tiny fraction of what actually exists throughout space and time. Every atom in your body, every photon striking your retina, every breath you take consists of ordinary matter that comprises less than 5% of universal mass energy, making all human experience a vanishingly small sample of cosmic reality, rather than the comprehensive picture our evolved intuitions suggest. This perspective transforms our species from central players in cosmic drama to brief flickering patterns of complexity emerging within vast oceans of invisible architecture, temporary arrangements of ordinary matter dancing through gravitational fields created by particles that remain forever beyond direct human perception. Yet paradoxically, this apparent cosmic insignificance becomes a source of profound significance when we recognize that consciousness itself represents perhaps the most extraordinary phenomenon in known physics: patterns of electrical activity within biological neural networks that somehow generate subjective experience capable of contemplating the very cosmic structures that gave birth to stellar nucleosynthesis and planetary formation necessary for life itself. The human brain contains roughly 86 billion neurons interconnected through trillions of synaptic connections, creating information processing networks whose computational capabilities enable mathematical reasoning about cosmic evolution spanning 13.8 billion years, while simultaneously generating the subjective experience of wonder when confronting galactic structures like Dragonfly 44 that challenge everything we thought we understood about universal architecture. This emergent property of organized matter allows the universe to become conscious of itself through human observation and theoretical reasoning, transforming invisible dark matter from merely an abstract concept in cosmological equations into a concrete reality that shapes galactic dynamics and determines whether planets like Earth can exist within stable stellar environments. Consciousness contemplating cosmic architecture represents an unlikely convergence between quantum mechanical processes operating within biological systems and gravitational phenomena spanning cosmological scales, suggesting deep connections between the microscopic and macroscopic realms that remain poorly understood despite centuries of scientific progress. The capacity for human minds to comprehend mathematical relationships governing dark matter physics while simultaneously experiencing subjective qualia associated with curiosity, awe, and wonder points toward fundamental questions about the nature of information processing in physical systems and whether consciousness emerges as an inevitable consequence of sufficient complexity or represents a rare accident that occurred only once within observable cosmic history. From this perspective, galaxies like Dragonfly 44 become more than simply collections of stars and invisible particles. They transform into natural laboratories where the universe experiments with different arrangements of matter and energy, while providing stable gravitational environments within which complex chemistry can unfold over billions of years to eventually produce self-aware systems capable of theoretical reasoning about their own cosmic origins. The invisible scaffolding that holds these galactic structures together extends its influence across scales ranging from individual particle interactions to cluster-scale phenomena, spanning hundreds of millions of light-years, creating hierarchical patterns of organization that connect quantum field fluctuations in the primordial universe to the emergence of biological complexity on countless worlds, be it scattered throughout cosmic space. This vast web of gravitational relationships ensures that every local process remains embedded within larger contexts that extend ultimately to cosmological horizons, making human existence simultaneously infinitesimal and intimately connected to universal evolution across all observable scales of space and time. The humility required to fully appreciate these cosmic perspectives demands acknowledgement that human knowledge remains incomplete and possibly fundamentally limited by the evolutionary history that shaped our cognitive capabilities for understanding middle-world environments rather than cosmic extremes involving invisible matter, curved space-time and quantum mechanical phenomena that operate according to mathematical principles rather than intuitive reasoning derived from everyday experience with macroscopic objects moving at modest velocities through familiar three-dimensional space. What is it about confronting the genuinely unknown that ignites something fundamental within human consciousness, transforming abstract mathematical equations and telescopic observations into sources of profound emotional resonance that connects our deepest sense of wonder to the ongoing quest for understanding cosmic mysteries like Dragonfly 4. The beauty inherent in scientific discovery emerges not from finding final answers, but from encountering phenomena so unexpected they force complete reconsideration of basic assumptions about reality, creating intellectual adventures that begin with puzzling observations and lead through chains of reasoning toward previously unimaginable territories of knowledge where each breakthrough reveals vast landscapes of additional mysteries waiting for exploration. This process transforms what initially appears as scientific failure into the greatest successes, because moments when established theories break down under the weight of new evidence provide gateways toward deeper understanding that would remain forever closed if observations simply confirmed existing expectations without challenge or surprise. The rotation curves that first revealed dark matter emerged from astronomers attempting to verify Newtonian mechanics on galactic scales, expecting to find confirmation of well-established physics, but instead discovering evidence for invisible matter that comprises the majority of universal mass-energy content. Similarly, the ultra-diffuse galaxies that now challenge our understanding of structure formation began as barely visible smudges in telescopic images, dismissed initially as imaging artifacts before revealing themselves as genuine cosmic structures, with properties so extreme they demand fundamental reconsideration of how galaxies form and evolve throughout cosmic history. Each apparent anomaly becomes a doorway through which human knowledge expands into previously unexplored regions of parameter space, where theoretical frameworks must stretch to accommodate observations that seem impossible according to established scientific wisdom. The essence of scientific progress lies precisely in this willingness to embrace uncertainty and follow evidence wherever it leads, even when discoveries challenge cherished theoretical constructs or force acknowledgement that current understanding represents merely preliminary sketches of cosmic architecture rather than complete blueprints for universal operation. Every answer extracted from careful observation and mathematical analysis reveals 10 new questions that could not even be formulated before the original mystery was partially resolved, creating cascading chains of inquiry that extend human knowledge into increasingly subtle and sophisticated appreciation for cosmic complexity. The discovery of dark matter opened entire new fields of particle physics, theoretical cosmology, and observational astronomy, while simultaneously revealing that visible matter represents less than 1/6 of total cosmic mass energy, fundamentally transforming our conception of universal composition from a straightforward collection of stars and gas into a predominantly invisible realm, governed by exotic physics operating beyond direct human perception. Ultra-diffuse galaxies like Dragonfly 44 continue this tradition by presenting combinations of properties that existing formation theories cannot explain, forcing development of new models that may eventually revolutionize our understanding of how cosmic structures assemble during early universal epochs when physical conditions differed dramatically from contemporary environments. The intellectual journey from initial puzzlement through theoretical development toward partial comprehension generates experiences that transcend purely rational analysis, engaging emotional and aesthetic sensibilities that recognize beauty in mathematical elegance, experimental precision, and conceptual breakthroughs that illuminate previously hidden aspects of natural order. This connection between scientific discovery and human wonder reflects deep evolutionary heritage that equipped our species with curiosity drives powerful enough to motivate exploration of environments far beyond immediate survival needs, enabling investigation of cosmic phenomena that operate across spatial and temporal scales, completely divorced from everyday human experience, yet somehow accessible through mathematical reasoning and instrumental observation. The capacity to find beauty in abstract theoretical frameworks and remote astronomical objects suggests fundamental connections between human consciousness and cosmic architecture that remain mysterious despite centuries of philosophical speculation and scientific investigation into the nature of mind and its relationship to physical reality. Wonder emerges as an essential component of human experience precisely because it motivates continued exploration, when practical considerations would suggest abandoning investigations into phenomena that offer no immediate benefits for survival or reproduction, yet may ultimately provide insights into fundamental questions about existence itself. The ongoing mystery surrounding dark matter exemplifies how science functions as exploration of the unimaginable rather than simple cataloguing of observable phenomena, requiring intellectual courage to pursue theoretical implications that extend far beyond direct empirical confirmation while maintaining rigorous standards for evidence and logical consistency that distinguish genuine scientific progress from mere speculation. Through this process, impossible objects like Dragonfly 44 become more than astronomical curiosities. They transform into invitations for expanding human consciousness toward cosmic scales, where invisible architecture governs visible phenomena according to mathematical principles that connect quantum mechanical fluctuations in primordial space-time to contemporary galactic structures spanning hundreds of thousands of light-years across billions of years of cosmic evolution. How do we return to that impossible galaxy floating in cosmic darkness, with minds now enriched by deeper appreciation for the profound mysteries it represents? Understanding that Dragonfly 44 serves as more than simply another astronomical object, but rather as a perfect metaphor for everything about existence that remains hidden from direct human perception, yet shapes every aspect of our cosmic story. When we first encountered this ghostly structure, 330 million light-years away, it seemed merely an anomaly that violated established physics, a cosmic mistake that should not exist, according to everything we thought we understood about galactic formation and evolution throughout universal history. Now, after journeying through rotation curves and dark matter halos, theoretical controversies and observational challenges, computer simulations and future telescopes, we recognize Dragonfly 44 as a profound teacher whose lessons extend far beyond astrophysics into fundamental questions about knowledge, mystery, and the human capacity to comprehend realities that transcend everyday sensory experience. This galaxy, constructed almost entirely from invisible architecture, becomes a cosmic mirror reflecting our own situation as conscious beings embedded within a universe where 95% of reality consists of phenomena that remain forever beyond direct observation, particles and energies that shape galactic destiny while flowing through our bodies without triggering the slightest sensation. You are made of star stuff, forged within nuclear phosphates that burned billions of years ago and scattered heavy elements into interstellar space, where gravity collected them into planets, oceans, and eventually biological systems capable of contemplating invisible galaxies across cosmic distances that light requires hundreds of millions of years to traverse. The carbon atoms forming your DNA, the calcium strengthening your bones, and the iron flowing through your bloodstream all originated within stellar cores where temperatures exceeded 100 million degrees, conditions so extreme they transformed primordial hydrogen into the periodic table of elements necessary for complex chemistry and biological evolution. Yet these familiar constituents of ordinary matter represent less than 1/6 of universal mass energy, making your physical existence a temporary arrangement of cosmic minority components dancing within gravitational fields generated by invisible particles that comprise the vast majority of everything that actually exists throughout space and time. Your consciousness emerges from neural networks containing more synaptic connections than there are stars within the Milky Way galaxy, information processing systems that somehow generate subjective experience while simultaneously enabling mathematical reasoning about cosmic evolution spanning 13.8 billion years from Big Bang nucleosynthesis to contemporary structure formation. This extraordinary capacity for self-awareness allows the universe to contemplate itself through human observation and theoretical understanding, creating feedback loops between cosmic architecture and conscious reflection that connect quantum mechanical processes within biological neural networks to gravitational phenomena operating across cosmological scales. Through your curiosity about impossible galaxies like Dragonfly 44, you participate directly in cosmic evolution as it develops mechanisms for understanding its own nature through emergent consciousness that arose within. Stable stellar environments made possible by dark matter scaffolding, extending across hundreds of thousands of light years. Every moment of wonder you experience while contemplating these cosmic mysteries represents a continuation of processes that began with primordial density fluctuations and evolved through hierarchical structure formation, stellar nucleosynthesis, planetary accretion, and biological evolution into conscious beings capable of theoretical reasoning about their own cosmic origins. The invisible cathedrals of dark matter that hold galaxies together also created the gravitational conditions necessary for star formation, heavy element production, and planetary system assembly that eventually led to the emergence of life, intelligence, and scientific understanding on at least one world orbiting an ordinary star within an unremarkable spiral galaxy. As we conclude this exploration of cosmic impossibilities and invisible architectures, remember that your journey into these mysteries continues every time you look up at night skies and wonder about the hidden realities surrounding every point of light scattered across stellar constellations. The questions we have explored tonight represent just the beginning of human inquiry into cosmic architecture, preliminary sketches of universal composition that future generations will refine, expand, and possibly revolutionize through discoveries we cannot yet imagine. Thank you for joining this expedition into cosmic darkness, where invisible matter shapes visible destiny, for bringing your curiosity and wonder to mysteries that connect human consciousness to universal evolution across all observable scales of space and time. In the darkness between galaxies, invisible cathedrals hold the universe together, and somewhere within their vast spans, conscious minds like yours continue the eternal quest to understand the magnificent cosmic architecture that gave birth to stars, planets, and the ongoing miracle of awareness contemplating its own impossible existence.